Welcome back to the channel, where we explore futuristic technologies shaping our world. Today, we're uncovering an idea straight out of science fiction: space-based solar power beaming clean energy directly to Earth. Imagine massive solar satellites capturing constant sunlight in orbit and transmitting power safely to the ground, day and night. How close are we to making this real, and what challenges remain? Stay tuned as we break it all down. And don't forget to subscribe right here today now. Number 5. Space collection. Space-based solar power begins with large satellites positioned in orbit, designed specifically to collect solar energy continuously. Unlike Earth-based solar panels, these systems are not affected by nighttime, seasonal changes, clouds, or atmospheric dust. In space, sunlight is available almost all the time, allowing satellites to harvest energy at much higher efficiency levels. These satellites are equipped with vast arrays of solar panels that can stretch across kilometers, capturing intense and uninterrupted solar radiation. The collected sunlight is immediately converted into electrical energy using advanced photovoltaic systems optimized for the harsh conditions of space. Because there is no atmosphere to filter or weaken the sunlight, energy capture is significantly stronger than on Earth. This makes space collection a highly reliable source of power generation. The orbital placement of these satellites is carefully selected to maintain constant exposure to the sun, often using geostationary or sun-synchronous orbits. Automated systems manage panel orientation to ensure maximum exposure at all times. Space collection also reduces land use conflicts, as no large areas on Earth are required for power generation. This stage forms the foundation of the entire system, as efficient energy capture in space determines how much usable power can ultimately be delivered to Earth. Without consistent and large-scale collection, the concept of space-based solar power would not be viable. Therefore, space collection represents the first and most critical step in turning sunlight from orbit into a dependable energy source for the planet. Number 4. Wireless transfer. Once solar energy is collected and converted into electricity in space, the next step is wireless transmission to Earth. This process involves transforming electrical energy into a focused energy beam, usually in the form of microwaves or lasers. Microwaves are commonly preferred because they can pass through clouds, rain, and the atmosphere with minimal energy loss. The energy beam is precisely controlled and directed toward a specific receiving location on Earth. Advanced beam-forming technology ensures that the transmission remains stable, accurate, and efficient over vast distances. Safety is a key consideration during wireless transfer, and power levels are designed to be non-harmful to humans, animals, and aircraft. The beam spreads slightly as it travels, reducing intensity and ensuring controlled delivery. Satellites use automated guidance systems and real-time tracking to keep the beam locked onto the correct ground target. This wireless method eliminates the need for physical cables or infrastructure stretching from space to Earth, which would be impractical. Energy transfer efficiency is continuously monitored and adjusted to minimize losses. The ability to transmit energy wirelessly from orbit to the surface is what makes space-based solar power feasible on a global scale. Without reliable wireless transfer, the energy collected in space would remain unusable, making this step a vital link between orbital generation and terrestrial consumption. Number 3. Ground reception. Ground reception is where space-transmitted energy is converted into usable electricity on Earth. This is achieved through large receiving stations known as rectennas, which are specially designed antenna arrays. Rectennas capture incoming microwave or laser energy and convert it directly into electrical current with high efficiency. These receiving stations are typically placed in open areas to ensure unobstructed energy capture. The design allows energy to be received safely, as the power density at ground level is kept low. Rectennas can be constructed using lightweight and cost-effective materials, making large-scale deployment feasible. Once the energy is converted into electricity, it is fed directly into local or national power grids. Ground reception systems are built with redundancy and monitoring systems to ensure consistent operation. Weather conditions have minimal impact on reception, especially when microwaves are used. The modular nature of rectennas allows capacity to be expanded as energy demand grows. This stage bridges space technology with existing electrical infrastructure, enabling seamless integration. Without efficient ground reception, transmitted energy would be wasted or unusable. Therefore, Ground reception plays a crucial role in turning space-based solar power into a practical and reliable energy solution for everyday use. Number 2. Clean power. Space-based solar power represents a major advancement in clean energy generation. Because it relies entirely on sunlight, it produces no greenhouse gas emissions during operation. Unlike fossil fuels, it does not release carbon dioxide, methane, or other pollutants into the atmosphere. This makes it a powerful tool in addressing climate change and reducing global dependence on non-renewable resources. Unlike many renewable sources on Earth, space-based solar power is not limited by weather or time of day, ensuring continuous clean energy supply. This reliability reduces the need for backup power plants that often rely on fossil fuels. Additionally, space-based systems avoid environmental damage such as deforestation, habitat destruction, or large-scale land use. There is also no risk of fuel depletion, as the sun provides an essentially unlimited energy source. Over time, this technology could significantly reduce air pollution and improve public health outcomes. Clean power from space also supports energy security by diversifying supply sources. As nations seek long-term sustainable solutions, space-based solar power stands out as a consistent and environmentally friendly option. Its ability to deliver large amounts of clean energy continuously makes it one of the most promising concepts for future global power generation. Number 1. Future scale. The future scale of space-based solar power has the potential to transform global energy systems. As technology advances, satellites can be built larger, more efficient, and more cost-effective. Mass production and reusable launch systems may drastically reduce deployment costs. In the long term, entire constellations of solar power satellites could supply energy to multiple regions simultaneously. This would allow power to be delivered to remote areas, disaster zones, and regions lacking traditional infrastructure. Future systems could dynamically redirect energy to where demand is highest, creating a flexible global power network. Advances in robotics and in-space manufacturing may enable construction and maintenance directly in orbit. This would further expand system scale without heavy reliance on Earth-based launches. As global energy demand continues to rise, space-based solar power could provide a stable backbone for worldwide electricity supply. It also opens possibilities for supporting energy-intensive technologies and future cities. The ability to scale beyond terrestrial limitations makes this concept uniquely powerful. At full maturity, space-based solar power could redefine how humanity generates, distributes, and consumes energy on a planetary level. Thanks for watching and spending your time with us as we explored space-based solar power and its potential to transform global energy. If you enjoyed this deep dive and want more future-focused content, show your support by liking the video, sharing it with others, and make sure to subscribe today.